Deviation from ideal gas behavior. What is this? Well, ideal gas, right? PV is equal to nRT, right? This is an ideal gas is one that behaves according to this equation. So as long as the temperature is high and the pressure is low, uh, you know, PV is equal to nRT. Now, if I rearrange it and solve for n, and I put in standard conditions, right, 1 atmosphere, 22.4 liter, 273 Kelvin, I'm talking about a mole of gas, 1 mole of gas. If I change the volume, change the pressure, change the temperature, doesn't matter, right? A mole of gas is a mole of gas. So, change the pressure, change the volume, change the temperature, it's still a mole of gas, right? So a mole is an amount. Change the pressure, change the temperature, change the volume, a mole of gas is a mole of gas. Well, looking at this curve, right, PV divided by RT is equal to a mole of gas. A mole of gas should be a mole of gas. But when I look at these real gases, as I start to put pressure on them, ammonia acts like less than a mole of gas. Well, why would that be? You haven't taken any particles out, right? But it's acting like less than a mole of gas. Methane starts to act like less than a mole of gas. But as you increase the pressure, right, both ammonia and methane, right, jump above the line and act like more than a mole of gas. Now, hydrogen, right off the bat, you start putting pressure on it, it acts like more than a mole of gas. So why would these gases not behave according to not behave in an ideal way? All right. Well, because they're real. Because the fact is, right, the assumptions we make about gases is that there's no intermolecular attraction and they don't take up space in the container. So looking at ammonia, so why would ammonia act like less than a mole of gas as you start to put pressure on it? Well, because it's a polar molecule, right? It's trigonal pyramidal shape, right? The nitrogen's more electronegative than the hydrogen. So there's a negative side and a positive side to ammonia. So as you start putting pressure on it, jamming these particles close together, all of a sudden, right, they start to liquefy, right? They start to act like, they stop acting like an ideal gas, right? They start attracting each other. So this attraction would cause the particles to hit the side of the container less hard, right? It's like someone holding your hand while you're trying to punch something, right? You're slowing it up. So as you're being pulled back from the side of the container, you're acting like less than a mole of gas. So how do we modify the ideal gas law to account for the fact that the pressure is lower than it should be, right, for something like ammonia? Well, there's this term we can subtract from the denominator, right? So if I make the denominator smaller, that'll bring the pressure back up. So there's a term that we subtract from the volume, right? And this will make the denominator smaller, make the pressure greater. N, it represents moles, and B is a constant, right? Every gas is going to have a different B value, right? Polar molecules are going to have a larger B value. Non-polar molecules are going to have a smaller B value, right? Smaller intermolecular attraction, larger intermolecular attraction. I should say larger, smaller, right? So ammonia would have a significant B value because it's a polar molecule. So I multiply it by the number of moles of gas I have, subtract it from the volume, and this will correct for the fact that it's acting like less than a mole of gas. Bring the pressure up. If we look at hydrogen, it's acting like more than a mole of gas right off the bat. Well, this is because molecules take up space in the container, right? Hydrogen's a very non-polar molecule, right? Hard to polarize, so very weak intermolecular attractions. So that's not the issue when you start putting pressure on it, right? There's very weak intermolecular attraction, so it's not going to act like less than a mole of gas. It's acting like more than a mole of gas because those hydrogen particles are taking up space in the container. Right, so with a gas, because they're so spread out, we say, oh yeah, the particle in the container really shouldn't count, right? It's so small compared to the space it's occupying. Well, if I crush them down, now all of a sudden, those hydrogens are significant, right? They take up space in the container. So the way we deal with this is by subtracting an A value times the ratio of mole squared divided by the volume squared. And this term will bring the pressure back down, right? So it's a jockeying between the two things, right? The Intermolecular attractions is making the pressure less. The fact that the particles take up space in the container is making the pressure more. So by putting in an A value and the B value, we can correct for the observed pressure, bring it back to more ideal behavior. This is called van der Waals equation. All right, so the B term is correcting for the intermolecular attraction. The A term is correcting for the fact that the particles take up space. So big particles would have a big A value, small particles have a small A value, and so on. The assumptions made in kinetic molecular theory: negligible volume of the gas molecules themselves, no attractive forces between the molecules, etc. Breaks down at high pressure and low temperature. So as long as they keep the pressure low and the temperature high, PV is equal to nRT will work. When I start bringing the pressures up and the temperatures down, all of a sudden it starts falling apart and I have to correct for it. So that's what the van der Waals equation is. One equation, right? There's a lot of equations that start correcting for non-ideal behavior, but this is just one. So again, the real gas, I kind of like this picture here, right? So again, the particles trying to hit the side of the container, but the intermolecular attractions are pulling it back. That's where the pressure's less. All right. If I crush these particles down, now all of a sudden they're taking up they're significant in terms of the space they take up. So that would make the pressure more, right? More collisions, less space, right? If I decrease the volume because of the particles take up space in the container, the pressure goes up. So taking up space raises the pressure. Attractions between the particle lower the pressure. All right, so here are some van der Waals constants, right? So helium has is the smallest gas particle, and it's very non-polarizable, so it has a very small A value and a very small B value. Whereas water, which is really polar, has a large A value. Still, it's a pretty small molecule, so a pretty small B value. Oh, okay. So I already answered it. Let's list two experimental conditions under which gases deviate from ideal behavior, right? So if you increase the pressure, this shoves the particles closer together. If you lower the temperature, right, those intermolecular attractions can't be ignored anymore because the particles are moving slower. So won't behave in an ideal way at high pressures, low temperatures. B, explain two reasons why gases deviate from ideal behavior. Well, because the gases take up space in the containers and the molecules attract each other. C, explain how the function of PV over RT can be used to show how gases behave non-ideally. Okay, so N should be a constant under all conditions. So if we have a gas acting like less than a mole of gas, this is due to intermolecular attractions. If we have a gas acting like more than a mole of gas, this is due to taking up space in the container. So negative deviation due to attractive forces, positive deviation taking up space in the container. Geez, I already answered these. I should have had them animated. Calculate the pressure that tetrachloromethane will exert at 40 degrees Celsius, 1 mole of gas occupying 33.3 liters. Okay, so we plug it in, right? PV is equal to nRT. We get how this gas would behave under ideal conditions. All right, so B. How does the gas behave under according to the van der Waals equation, right? So when we shove those constants in, along with the volume and the number of moles, and we correct for the fact that tetrachloromethane takes up space in the container and it has intermolecular attractions, we end up with a slightly lower value than we do from ideal behavior, right? So in an ideal gas, it's supposed to have a pressure of 0.773 atmospheres. Using the van der Waals equation, it has a little bit less. So what would cause this? Well, the fact of the matter is, chlorine is a big puffier atom than, say, hydrogen is or something. So you're going to have significant intermolecular attractions, right? This was what would cause a gas to act like less than a mole of gas. So the A term for, or I should say the B term for tetrachloromethane is significant, right? So stronger intermolecular attractions make this particle act like a little bit less than a mole of gas.